Welcome to Piscribe's review of electric current, resistance, and Ohm's law. In this unit, we are going to walk through 10 multiple-choice questions together, and I want to set a single expectation before we begin. Every question in this set looks like a number-crunching puzzle, but it isn't. Every question is hiding one physical idea, and the job is to name that idea before you touch a single formula. If you can say the name out loud, the arithmetic almost writes itself. Now let's look at the through line. These 10 questions split cleanly into 4 recurring moves, and once you see the pattern, you'll start recognizing it on sight. First, potential dividers, that's questions 1 and 2, a uniform wire with a sliding contact, a voltmeter across the engaged length. The classic trick there is a short across part of the wire, which breaks the divider at that point. Second, Ohm's law applied to a single branch, questions 3, 4, and 7. Temperature coefficient of resistance, a non-ideal voltmeter drawing current, drift velocity, same V equals IR shape, just dressed up differently. Third, equivalent resistance of networks, questions 5, 6, 8, and 10. Series parallel rules, yes, but more importantly the symmetry shortcut. Equipotential points carry no current, so any resistor between them can be removed. Fourth, geometry changes the resistance, that's question 9, where doubling a rod at fixed volume quarters the area. So R scales as L squared, not L before we start. Let me also plant the vocabulary in your head, because every voiceover that follows will use these words in exactly this way. Resistance is rho L over A, length up means R up, area up means R down. Ohm's law, V equals IR, holds for any ohmic conductor at constant temperature. The temperature coefficient form is R sub theta equals R0 times 1 plus alpha theta for small temperature changes around a reference. Drift velocity is V sub D equals I over A NE, the slow average motion of electrons behind the current. And equipotential points are points held at the same potential by symmetry, by a balanced bridge, by an equal arm divider, and the wire between them is dead weight. Keep those 5 phrases loaded, because we'll be using them on every single slide from here on. Now let's talk about the recurring techniques that will save you time on the exam, and the first one is the most important. Name the principle before the formula. Before you write a single number down, write one line about what kind of problem this is. Is it a potential divider, a single branch Ohm's law, a symmetry reduction, an equipotential shortcut? The moment you can say this is a balanced bridge, so the bridge resistor is irrelevant, the question is mostly over. The opposite move, reaching for the calculator first, is where most of the silly mistakes live. The second technique, specifically for networks, is to look for a symmetry line before you grind series parallel combinations. If the diagram is mirror symmetric, draw the line. 2 points on that line sit at the same potential, the resistor between them is dead, and you can remove it. The rest of the network usually collapses into a single series parallel chain. We will use this trick 3 or 4 times in this unit, and once you see it, you will never unsee it. And finally, how to use this unit. Read the question, pause to predict the shape of the answer in your head. Is it a line, a curve, a fraction, a number? Then read the rewritten solution. The aim is not just to memorize answers. The aim is to build the habit of naming the principle before reaching for numbers. By the time we finish the last question, that habit should be automatic. Let's get into it. Here is question 1, and it's a potential divider with a twist. Take a look at the diagram. AC is a uniform resistor wire, same resistance per unit length all the way along. A voltmeter V sits in parallel with whatever segment of the wire is between the slider D and the left-hand end. A, we move the slider D from A all the way to C, while points B and C are connected by a short. The question asks, how does the voltmeter reading V vary as the slider moves? Which of the 5 graphs on screen is the right shape? Before I show you the answer, take a moment to predict it. You're going to watch a slider move along a uniform wire, and the voltmeter is reading the potential drop between the slider and one end. The first thing to ask yourself, what does a uniform wire connected across an ideal cell do to the current? It carries a constant current. And if the current is constant, the drop across any engaged length is proportional to that length. So as the slider moves, you'd expect a straight line through the origin. But here's the twist. The short between B and C, what does a short do to the potential at the 2 ends? It forces them to be equal. So the moment the slider passes B, the potential can't drop any further. It just stays flat all the way to C. Keep that picture in mind, a rising line that flattens out. We'll see which graph that is next. And the answer is option 3. Here's the reasoning. A uniform wire connected across an ideal cell carries a constant current, and the drop across any engaged length is proportional to that length. So a slider moving along a uniform wire traces a straight line through the origin in V versus L. So far, so obvious. The twist is the short between B and C. A conducting wire of negligible resistance between 2 points forces them to the same potential. From B onwards, the voltmeter cannot pick up any further drop. The potential stays flat at the B value all the way to C. So the voltmeter reading rises linearly from A to B, then stays constant from B to C. That shape is option 3. The lesson here is bigger than this one question. Whenever you see a short across part of the wire on a potential divider, your first move is to ask, what points does the short force to the same potential? The answer tells you where the divider breaks, and the graph shape falls out of that one observation. Resist the urge to compute. First name the principle, then let the arithmetic follow. Question 2 is another potential divider-looking question, but it's really testing something different. It's testing whether you understand what a rheostat is doing in the circuit. Let me set the scene. We have a uniform wire of length L connected between terminals P and Q. An ammeter A sits in the main loop. A voltmeter V is connected in parallel across the wire between P and Q. And somewhere in series is a rheostat. The question says the ammeter reading is kept constant by adjusting the rheostat as we change L, so we vary the length of wire in the circuit. And someone is constantly fiddling with the rheostat to keep the current at the same value. As L changes, how does the voltmeter reading V change? Before you peek at the answer, predict the shape. The wire's resistance is ρ times L over A, that grows linearly with L. The current is held constant by the rheostat. The voltmeter is reading V equals I times R, and R is growing linearly with L, so V should grow linearly with L. Keep that in mind. Linear through the origin. Now let's see which option that is. The answer is option 1, a straight line through the origin, V increasing linearly with L. Here's why. The rheostat is the key phrase in this question. As the engaged length L of the wire grows, the wire's resistance R equals ρ L over A grows with it. Without intervention, the circuit current would drop. The rheostat is being continuously adjusted down so that the current in the loop is held constant. With I fixed, Ohm's law gives V equals I times R, which is I times ρ L over A. Since I, ρ, and R are all constant, V is directly proportional to L. The graph is a straight line through the origin. Option 1. Now here's the trap to avoid. Do not confuse this with the situation where current is allowed to fall. If I were not held constant, V would still be linear in L because both R and V scale with L, but with a different slope that the question would not call out as kept constant. The word kept is doing real work in this stem. When the question explicitly tells you current is held constant, treat that as a given, not a side comment. It collapses the problem into one line. This is a question where reading the stem carefully saves you a calculation. Question 3 is a one-line solve once you recognize the principle. Here's the setup. A platinum wire coil has a resistance of 50 ohms at 0 degrees Celsius. We dunk it in melting lead, and the resistance climbs to 115 ohms. The temperature coefficient of resistivity of platinum is given as 4 times 10 to the minus 3 per degree. See the question. What is the melting point of lead? Before we crunch, name the principle. The temperature coefficient of resistance formula applies here. For small temperature changes, the resistance of a metal varies linearly. R sub theta equals R0 times 1 plus alpha theta. We have R0, we have R sub theta, we have alpha, we just need to solve for theta. One line of algebra, let's do it. And the answer is option 2, 325 degrees Celsius. Here's the working. For small temperature changes around a reference temperature, the resistance of a metal varies linearly. R sub theta equals R0 times 1 plus alpha theta. Here R0 is 50 ohms at theta equals 0 degrees, and R sub theta is 115 ohms at the unknown lead melting point theta. Substitute and isolate theta. 115 equals 50 times 1 plus 4 times 10 to the minus 3 times theta. Distribute. 115 equals 50 plus 0.2 theta. Subtract 50 from both sides. 65 equals 0.2 theta. Divide. Theta equals 65 over 0.2, which is 325 degrees Celsius. The initial temperature is 0, so the lead is melting at 325. Option 2. Now here's the memorable shape. Resistance up means temperature up. The factor 1 plus alpha theta is just a linear ramp with slope alpha R0, anchored at R0. Whenever you see two resistance readings and a temperature coefficient, you are looking at a one-line solve. Don't get fancy. Don't reach for Kelvin conversions if the question is in Celsius. The formula works in Celsius as long as the reference is 0 degrees. This is one of those questions where the answer should pop out in under a minute if you trust the formula. Question 4 is a classic trap question. The stem is just 4 words. Current across the voltmeter is followed by 5 numerical options, but the diagram is the whole story. A 12-volt cell is in series with an 800-ohm resistor. After that, there's a parallel combination of another 800-ohm resistor and a voltmeter. And crucially, the voltmeter is labeled 800 ohms. So this voltmeter is not ideal. It has the same resistance as the resistor it's sitting in parallel with. The question is asking how much current flows through the voltmeter branch specifically. Look at the diagram and predict before I show you the working. The whole current leaves the cell, splits at the junction, and you need to know how it splits between the 800-ohm resistor and the 800-ohm voltmeter. Two equal resistances in parallel, what do you expect the split to look like? The answer is option 3, 5 milliamps. The trap in this question is the word voltmeter. A real voltmeter has a large but finite resistance. Here it is given as 800 ohms, the same as the resistor in parallel with it. So the voltmeter does draw current, and you cannot use the ideal voltmeter shortcut. Let's walk through the 4 steps. Step 1, total resistance. The first 800 ohms is in series with the parallel pair, which is 800 in parallel with 800 equals 400 ohms. So our total equals 800 plus 400, which is 1,200 ohms. Step 2, total current from the cell. Ohm's law on the whole circuit. I equals V over R equals 12 volts over 1,200 ohms, which is 10 milliamps. That matches the 10 milliamps leaving the positive terminal in the diagram. Step 3, voltage across the parallel pair. The first 800 ohms drops 10 milliamps times 800 ohms equals 8 volts, leaving 12 minus 8 equals 4 volts across the parallel combination. Step 4, current through the voltmeter. With 4 volts across its 800 ohms, IV equals 4 over 800, which is 5 milliamps. The matching 800 ohm resistor in parallel also takes 5 milliamps, so the two branches of the parallel pair share the 10 milliamps total exactly equally 5 milliamps through the voltmeter. The trap to avoid is option 1, current is 0, which is what you would pick if you silently treated the voltmeter as ideal. Always check the resistance given for a meter in the diagram before assuming it draws no current. If a number is printed next to a voltmeter symbol, that number is the meter's resistance, and it matters. Question 5 is a network question, and the moment you look at the diagram you should be thinking one word, symmetry. 12 resistors of 1 ohm each, arranged in a diamond pattern between terminals X and Y. The 5 options are all simple fractions, 2/3, 3/4, 1, 4/3, 3/2. The diagram looks dense, but here's your first move on any network that looks like a sea of resistors. Look for a symmetry line before you start grinding series parallel combinations. And this one has a vertical line of mirror symmetry right through the middle. That single observation is going to collapse the whole problem. Predict the answer in your head before I show you the working. If 2 points sit on the symmetry line, what does that tell you about their potentials? And if they're at the same potential, what can you do with the resistor between them? The answer is option 2, 3/4 of an ohm. Here's the reasoning step by step. When a network looks like a sea of resistors, look for symmetry first. Here the diamond between X and Y is mirror symmetric across a vertical line through the middle. Any 2 points sitting on that line are at the same potential whenever a voltage is applied across X, and Y. Step 1, kill the symmetric resistors. The 2 resistors that cross the symmetry line carry no current, because the points at their ends are equipotential. Remove them. Step 2, identical halves in parallel between X and Y. What remains is 2 identical networks, call them XP and YP, that meet at the equipotential node on the symmetry line. Each half is a path from X or Y to that midpoint. Because both halves share the same pair of terminals X to midpoint and Y to midpoint, they are in parallel with each other. Let me show you the diagram that walks this reduction panel by panel, and then we'll carry the arithmetic to the end. Take a look at the diagram on screen. It walks the full simplification in one image, reading left to right. The left panel shows the original 12-resistor diamond with the symmetry axis marked. The middle panel shows the 2 symmetry line resistors removed, and notice how the network already looks like 2 parallel branches. The right panel shows each branch reduced to its half resistance, and the total lands at 3/4 of an ohm. The walkthrough on this slide is the visual companion to the reasoning I just gave you, same story. But now you can see the network collapse stage by stage. Notice how each merge removes 1 level of complexity, and the final picture is just 2 equal resistors in parallel. Keep that visual in mind for similar problems, symmetry first, then series parallel, and the dense-looking network becomes a single line of arithmetic. Now let's carry the reduction through to the final number. Step 3. Reduce 1/2. 1/2 consists of a 1 ohm resistor in series with a parallel pair of two 1 ohm resistors. The parallel pair is 1 times 1 over 1 plus 1, which is 1/2 ohm. Then the half is 1 plus 1/2, which is 3/2 ohm. Step 4. Combine the two halves. Each half has 3/2 ohm, and they sit in parallel between x and the midpoint, and between the midpoint and y, so Rxy equals 3/2 times 3/2 over 3/2 plus 3/2, which is 9/4 over 3, which is 3/4 of an ohm. That is option 2. The transferable insight is worth holding onto. Anytime a network looks like it was drawn by stacking mirrored halves, draw the symmetry line first. 2 points on that line sit at the same potential, and the wire between them is dead weight. Remove it, and the rest of the network usually collapses into a single series parallel chain. We are going to use this exact move again in question 10, so file it away. Question 6 is a geometry question with a wire ring. Here's the setup. A circle of radius r, with a diameter ob drawn straight across through the center O. Both the ring and the diameter are made of the same wire, with resistance per unit length ρ. The question, what is the resistance measured between A and the center O? Look at the answer options. They are all of the form something times r times ρ, and the something involves pi. That should already tell you the answer. We'll use the circumference 2 pi r somewhere. Before I show you the working, take a moment to look at the figure and predict. What symmetry is at play here, and how many distinct paths can current take from A to O? The answer is option 1, the bracket pi plus 2 over pi plus 4 all times r ρ. Here's the reasoning. The figure is symmetric about the diameter ob. The two halves of the diameter are equal, so call each half's resistance r sub minus 1. The two semicircular arcs are also equal, so call each one's resistance r sub minus 2. With ρ as the resistance per unit length, r sub minus 1 is r ρ, that's the half diameter of length r. And r sub minus 2 is pi r ρ. That's the semicircle of length pi r. The simplification diagrams on the next two slides show how the four segments, two half diameters and two semicircles reduce, between A and O, to a configuration in which the standard parallel formula applies. Let me walk you through those diagrams, and then we'll carry the algebra to the final answer. Two reduction stages sit side by side on this slide. The top image shows the original geometry on the left, and the same geometry on the right with r sub minus 1 on each straight segment and r sub minus 2 on each curved segment. Naming the segments by resistance is the move that turns this from a geometry problem into a circuit problem. The bottom image shows the second stage. Collapse each labeled segment to a single resistor, then identify the parallel pair of r sub minus 2 on the upper semicircle path and the lower semicircle path. The series of parallel chain r sub minus 1 in series with the two r sub minus 2 in parallel is now explicit. Notice the visual symmetry between the two top halves. The parallel structure emerges naturally once you label the segments. From here, it's just a textbook parallel formula, which will apply on the next slide. Carrying the reduction through to the final equivalent resistance between A and O. The equivalent resistance between AO equals 2 r sub minus 1 squared plus r sub minus 1 r sub minus 2, all over 4 r sub minus 1 plus r sub minus 2. Substituting r sub minus 1 equals r rho and r sub minus 2 equals pi r rho, we get 2 r squared rho squared plus r rho times pi r rho over r rho times 4 plus pi. The numerator is r squared rho squared times 2 plus pi. The denominator is r rho times 4 plus pi. Dividing the r rho cancels 1 power, leaving pi plus 2 over pi plus 4, all times r rho. That is option 1. The transferable insight is this. Resistive geometries are built from a small catalog of moves: straight wire with r equals rho L over A, circle with pi r of length, series with r sub minus 1 plus r sub minus 2, parallel with r sub minus 1 r sub minus 2 over r sub minus 1 plus r sub minus 2. When you see a wire ring with a diameter, identify the parallel paths by symmetry and apply the catalog without second guessing. The pi plus 2 over pi plus 4 shape is a fingerprint of two parallel arcs plus a straight wire in series. Once you've seen it once, you'll recognize it on sight. Question 7 is a drift velocity calculation pure formula recall. Here's the setup. A uniform copper wire of cross-sectional area 10 to the minus 7 square meters carries a current of 1.6 amps. The free electron density of copper is 10 to the 29 per cubic meter, and the electron charge is 1.6 times 10 to the minus 19 coulombs. The question asks, what is the drift velocity of the electrons? The options are millimeters per second, ranging from 1 to 20. Before we plug in numbers, here's the principle. Current is the rate at which charge crosses a section of wire, and the speed at which the charge carriers themselves move is the drift velocity. Predict the order of magnitude. Current of 1.6 amps sounds fast. But how fast do you think individual electrons actually move in a real wire? The answer is option 1, 1 millimeter per second. Here's the working. Current is the rate at which charge crosses a section of wire. If N is the free electron density of the cross-sectional area, E the electron charge, and V sub d the drift velocity, then in 1 second a length V sub d of the electron column sweeps through the section. So I equals N a E V sub d, which rearranges to V sub d equals I over A N E. Plug in the numbers. V sub d equals 1.6 over 10 to the minus 7 times 10 to the 29 times 1.6 times 10 to the minus 19 in meters per second. Combine the powers of 10 first. 10 to the minus 7 times 10 to the 29 times 10 to the minus 19 is 10 to the 3. Combine the 1.6's in numerator and denominator, they cancel exactly. That leaves 1 over 10 to the 3 meters per second, which is 10 to the minus 3 meters per second, or 1 millimeter per second. Option 1. Here's the punchline, and it is the memorable part. A current of 1.6 amps sounds fast, but drift velocities in real wires are astonishingly slow millimeters per second. The current is fast only because there are enormous numbers of charge carriers all drifting together. The electrical signal travels through the wire at close to the speed of light. The electrons themselves crawl. That contrast signal at light speed, electrons at millimeters per second, is one of those facts that, once you internalize it, makes intuitive sense of the whole topic. Question 8 is a parallel serial network reduction. The diagram shows terminals A and B with a stack of parallel branches between them, reading from top to bottom. A top branch with a 6-ohm resistor in series with a 2-ohm resistor, then 2 parallel 12-ohm branches, then 2 parallel 2-ohm branches, then a bottom 12-ohm branch. The question is the equivalent resistance between A and B. Options range from 2 ohms to 10 ohms. Before we start, here's your strategy. When a network has several parallel branches between the same two terminals, simplify one branch at a time and then combine the reduced branches in parallel. Never grind the whole thing at once. Find merges, then chain them. There's also an arithmetic shortcut worth memorizing. 2 equal resistors in parallel give half of 1. No need for the full R-1 R-2 over R-1 plus R-2 formula. That's the move that will keep each of these branches to one step. Let me show you the working. The answer is option 2, 4 ohms. Here's how to think about the reduction. 2 equal resistors in parallel give half of 1. That's the shortcut. For this network, the top branch is a 6 ohm in series with a 2 ohm, which reduces to 8 ohms. 2 12-ohm branches in parallel reduce to 6 ohms. 2 2-ohm branches in parallel reduce to 1 ohm. The bottom 12-ohm branch stays at 12 ohms. So now you have 4 branches in parallel, 8, 6, 1, and 12. Combine them in parallel, and that's where the chain of merges technique comes in. Let me show you the diagram on the next slide that walks the full reduction panel by panel. The diagram on this slide walks the full reduction in one image. Reading left to right, each panel shows one merge. Panels 1 to 2 show the first parallel collapse. The topmost 6 ohm in parallel with 12 ohm collapses to 4 ohms. Panels 2 to 3 show the first series collapse. 4 ohms in series with 2 ohms combined to 6 ohms, and that branch is now in parallel with the next 12-ohm resistor. Panels 3 to 4 show the second parallel collapse. 6 ohm in parallel with 12-ohm collapses to 4 ohms. Panels 4 to 5 show the second series collapse. 4 ohms in series with 2 ohms combined to 6 ohms in parallel with the next 12-ohm. Panels 5 to 6 show the third parallel collapse. 6 ohm in parallel with 12-ohm collapses to 4 ohms. Panels 6 to 7 show the third series collapse, 4 ohms in series with the final 2 ohms combined to 6 ohms, in parallel with the last 12-ohm branch. And the final panel solving 6 ohms in parallel with 12 ohms yields the final equivalent resistance of 4 ohms. Notice the rhythm. Every 2 panels is one cycle of parallel collapse then series merge, and that rhythm keeps the working manageable. Don't try to hold the whole network in your head at once. Walk through it one merge at a time. That is option 2, 4 ohms between A and B. The transferable insight is this. For networks where many branches share the same pair of terminals, reduction is a tree of merges, not one big calculation. Reduce each branch to a single number first, then combine those numbers in parallel. When the work solution diagram is dense, walk through it panel by panel rather than trying to hold the whole network in your head. Each panel shows a single merge and the merges chain. This is the same idea we used in question 6. By the way, both problems reward you for collapsing subnetworks one at a time and combining the results. File that pattern away. Question 9 is a geometry-changing question, and the stem is short. A new cylindrical rod of length 2L is made by using a cylindrical copper rod of length L. How does the resistance of the new rod compare to the initial rod? The options are twice, half, 4 times, 1/4, or equal. Here's the trap: many students see double the length and answer double the resistance. But before you fall for that, ask yourself, is the volume of copper conserved? The new rod is made by using the original rod, same copper, same mass, same volume. So if the length doubled, what must have happened to the cross-sectional area? Predict the answer in your head before I show you the algebra. The answer is option 3, 4 times. Here's the working. The phrase "made by using a cylindrical copper rod of length L" means the new rod contains exactly the same copper, same mass, same density, same volume. Step 1: volume is conserved. If the new length is 2L, the new cross-sectional area must be A over 2. V equals A times L equals A over 2 times 2L. Both sides equal the original volume. Step 2: apply R equals rho L over A since rho is unchanged. R new equals rho times 2L over 2, which is 4 times rho L over A, which is 4 times R initial. The resistance is quadrupled, option 3. Now here's why this trips people up. Many students see double the length and answer double the resistance. That ignores the area halving. Whenever a rod is stretched or compressed, the right question to ask first is the volume fixed? If yes, area scales as 1 over L and resistance scales as L squared. Stretching the rod by a factor of 2 gives a factor of 4 in resistance. The transferable insight is worth memorizing. Resistance scales as L over A is the literal form, but resistance scales as L squared for a fixed volume rod is the practical form. Memorizing the second saves a step on every geometry-changing question. Question 10 is the final network question, and it is a beautiful example of the equipotential trick in action. The diagram shows a voltage source V connected across terminals A and C, with 4 resistors of resistance R forming a Wheatstone bridge-like configuration. 2 resistors are in parallel between A and B, 2 in parallel between D and C, and a single resistor sits between B and D. The question asks for the effective resistance, seen by the source across AC and also across BD. And those are 2 different numbers, so we have to do them separately. Before we crunch, name the principle. The 4 corner resistors form a Wheatstone bridge. When is a bridge balanced? When the ratio of resistances on one side equals the ratio on the other. If it is balanced, the midpoints sit at the same potential, and the bridge resistor carries no current. Predict the answer for both halves. The answer is option 5, R across AC and infinity across BD. Here's the reasoning broken into pieces. First, what the question is actually asking. Effective resistance seen by the source across AC is the equivalent resistance the source feels between its own terminals A and C. Effective resistance across BD is the equivalent resistance between B and D. The resistance an additional voltmeter would measure if connected across those midpoints. Step 1. Recognize the bridge. The 4 corner resistors, 2 pairs of R between A and B, 2 pairs between D and C, with a single R between B and D, form a balanced Wheatstone bridge. The condition for balance is ROB over RBC equals RAD over RDC, and here both ratios are 1. In a balanced bridge, the midpoints B and D sit at the same potential, so the bridge resistor between them carries no current. It can be removed without changing anything. That's the same equipotential move we used in question 5, just dressed up as a Wheatstone bridge. Let me finish the calculation on the next slide. Step 2. Effective resistance across AC. With the bridge resistor gone, the 2 parallel pairs in series give RAC equals R over 2 plus R over 2, which is R the source sees R. Step 3. Effective resistance across BD. Because B and D are held equipotential by the source, no current flows between them regardless of how the source voltage is set. To a hypothetical source connected between B and D, the network appears as an open circuit, so RBD equals infinity. That is option 5, R across AC and infinity across BD. The transferable insight is the one I want you to walk away with. A balanced bridge is the same idea as the equipotential symmetry used in question 5. Points at the same potential mean the wire between them is dead. Whenever 4 resistors form the arms of a bridge, check the ratio R-1 over R-2 equals R-3 over R-4 before doing any arithmetic. If it holds, the bridge resistor is irrelevant. This trick will save you minutes on a Wheatstone bridge problem, and it generalizes to any network where you can spot a balanced configuration. Trust the equipotential move. We have come to the end of the 10 questions, and now is a good moment to zoom out. 10 problems, 4 underlying ideas. The arithmetic changed every time, but the physics did not. Let me give you the 3 principles I want you to keep, and then list the common traps we have already seen in this set. Principle 1. Name the principle before the formula. Every question in this unit was one of 4 kinds: a potential divider, an Ohm's law application, a series parallel reduction, or a symmetry or equipotential shortcut. Saying the name out loud saves the wrong arithmetic. The first 10 seconds on any problem are not for the calculator, they are for naming what kind of problem this is. Principle 2. Symmetry is the first move on any network. If the diagram is mirror symmetric, draw the line. If 2 points sit at the same potential by construction, a balanced bridge, the midpoint of a voltage divider with equal arms, kill the resistor between them. This move turned the 12-resistor diamond into a one-line calculation, and it turned the balanced Wheatstone bridge into 2 simple parallel pairs. Use it. Principle 3. Always check what is conserved. When a wire is stretched, the volume stays constant, so it scales as 1 over L and R scales as L squared. When a rheostat is described as keeping current constant, treat that as given, not as a side comment. Conservation laws are the hidden assumptions in every problem, and naming them up front saves the wrong arithmetic. Now the common traps we have seen in this set. Treating a voltmeter as ideal when its resistance is given. Reading double the length and answering double the resistance without noticing the area halved. Forgetting that a short across part of a uniform wire flattens the potential there, and reaching for series parallel arithmetic before checking for a balanced bridge. Every one of these traps cost someone a mark in the past. Don't let them cost you ones. And finally, here is your revision guidance. If you want to lock these ideas in long-term, reattempt from memory in this order with the answers hidden. First, the drift velocity calculation, that is pure formula recall. Second, the temperature coefficient melting point, one-step algebra. Third, the 12-resistor diamond symmetry reduction. Fourth, the balanced Wheatstone bridge, identify the ratio, kill the bridge resistor. And fifth, the potential divider with a short across B to see graph shape. That order goes from pure recall to multi-step reasoning, so the difficulty curve is gentle. If any of these take more than 30 seconds of staring, return to the relevant lesson and rederive, not reread. Rederiving builds storage strength. Rereading builds familiarity, which feels like knowledge but fades fast. For further study, the references on screen are the 4 high-trust sources behind this unit.